learningspace.com.ng.
Welcome back to our 10 days marathon journey to your success in JUPEB examination. Today I'll continue with Physics 002 that involves heat, waves, and optics. If you remember the last time, we end our question in question 3. So we'll be heading to question 4. The likely questions that you are likely to find submit in the examination. If you don't see it this way, you will see something very close. Now, this question 4AI states that describe with suitable examples the dual wave particle behavior of X-rays and electrons. So this has to do with wave particle duality of matter. The wave particle duality of matter is actually a phenomenon that illustrates that particles or particles exhibit wave nature, wave exhibit particle nature. If you are talking about wave particle duality of light, it's a phenomenon that explains that light exhibits both wave and particle nature. If you are talking about wave particle duality of matter, such as electron, it means that electron as a matter also exhibits wave nature. Okay, we are to use a suitable example to describe the dual wave particle behavior of X-rays and electrons. Now, as per X-rays, it was exhibited by Arthur Compton in Compton's scattering that X-rays also exhibit particle nature. When X-ray light is being incidented on an electron of a particular metal, and as a result of incident of that X-ray, there is reduction in the frequency of the deflected light and increase in wavelength as something that is likened to collision between two particles, one being the free electron and the other being the photon, as illustrated by Compton in the Compton scattering. In the Compton scattering, it was indicated that let's assume that this is the incident ray that has a photon. The incident photon incidented on an electron, let's say at rest. Okay, this incident ray has initial wavelength lambda I. Now, on incidenting on the electron, there is a deflected ray with higher wavelength. That is, let's call this one the final wavelength. So then there is this recoil electron. So now the incident photon, which is from the X-ray, it has a wavelength. Then it was discovered that the scattered photon that is deflected has a higher wavelength. The final wavelength is greater than the initial wavelength, meaning that there is alteration in the energy. If the final wavelength is higher than the initial wavelength, it's like the energy is slightly reduced. And what does it mean for energy to be reduced? Imagine you running on the road and you just stumble on something. You know, there's every tendency that your energy will reduce because of what you stumbled on. And for this Compton scattering, so for the difference in wavelength, we'll call it Compton shift, which is the final wavelength minus the initial wavelength. Okay, and this gives us H all over m mass of electron C into bracket 1 minus cos theta. That theta is the angle through which the deflected radiation is being deflected. Okay, this is the angle through which the electron is being recoiled. So this is the content shift. This displays that X-ray as part of electromagnetic spectrum also exhibits what? Particle nature. Now, for the case of electron diffraction, that is what we call electron diffraction and interference effect that occur due to wave-like nature of beam of electrons when passing near a particular matter. Louis de Broglie proposed that electrons and other particles have wavelengths, and the wavelength is inversely proportional to their momentum. Like the wavelength of every other particle is inversely proportional to their momentum, P being momentum. Thus, it means that they are combining both what? Wave and particle nature. If you introduce a constant, this gives us a Planck constant all over the momentum, and the momentum is mass times velocity. So the wavelength means is the content the Planck's constant divided by mass times velocity. So that explains that question. Let's move down to question number 4A I. Number 4A states that you should list 3 features of photoelectric effects that are not consistent with simple wave theory of light. Okay, these 3 features of a photoelectric effect that is not consistent with simple wave theory of light include: number 1, absence of lag time; number 2, independence of kinetic energy of electrons, that is the photoelectrons. Are we there? On the intensity of incident radiation. Number 3, presence of a cutoff frequency, cutoff or threshold frequency. Now let me explain these 3 concepts. Now, in photoelectric effect, wave theory explains that electrons are emitted after a short period of time when light falls on a substance, on certain particular substance, right? However, in photoelectric effects, emission is instant. Now, the fact that for the wave theory there's supposed to be lag time, little time before the electrons will be emitted, is not consistent with the photoelectric effect that stated that emission, once the light got to threshold frequency, it has to be instant. Now, the second one, there is the independence of kinetic energy of photoelectrons on the intensity of the incident radiation. Wave theory explains that as wave energy increase with increase in intensity, that wave energy increase with increase in intensity. However, for photoelectric effect, increase in intensity will only increase the number of electrons emitted. It has no effect on the energy of the electron emitted. Then the third one is the presence of the cutoff frequency. Now, the wave theory explains that the electron that is being emitted is independent on the frequency of the incident radiation. However, for photoelectric effect, the light intensity, the light that is being incidented on the surface of the particular metal will have to reach the threshold frequency or the cutoff frequency before electron can be emitted. So these three features, they are inconsistent with the wave theory. Okay, now let's move down to the next question. Question 4a states that you should write the equation of ratio of de Broglie wavelength of electron to the minimum wavelength of X-ray produced in an X-ray tube. Okay, we all know that in an X-ray tube, there is beam of electron, high energy electron that is being incident from the cathode on the targeted metal, and that will cause electrons to be knocked off and at the same time X-ray to be produced. Now, so what is the minimum wavelength of these what is the de Broglie wavelength of this electron? Now, the de Broglie wavelength of the electron is equals to the Planck constant divided by mass of electron times velocity of electron. And we all know that alpha, the kinetic energy that the electron processed, which is half mv squared, is equals to charge on electron times the potential difference that is applied across the terminal of the electrode. Now, if we make this velocity subject of the formula, we are going to have 2 eV divided by mass of electron all square root. The capital letter V here is the potential difference that is applied. This V here is the velocity. If we substitute it in this formula, we are going to have the wavelength of the electron to be h all divided by m, and the V is this man here. 2 charge on electron, voltage all over mass of electron. Now, if I am to take this mass inside the square root, I can rewrite this mass as m squared then square root. Okay, so n squared square root will still give you the same thing as m dot square root of 2 charge on electron, the voltage apply all over mass of electron. So if I decide to take this into the square root, I will have the de Broglie wavelength of the electron to be charge on electron all divided by square root of m squared dot 2ev all over m. So this will cancel this. So the de Broglie wavelength of the electron is the Planck constant all over square root of 2 mass of electron, charge on electron, the potential difference apply across the terminal. This is the de Broglie wavelength of electron. Of electron. Though in your examination it is not necessary that you show all this derivation provided you know this formula readily, but you know sometimes you may just forget the particular formula, then you start from the scratch for the derivation of the electron, then you get your formula, then you now apply it. Now the X-ray that is being produced, it has this energy which is hc, which is the speed of light all over the wavelength of that's minimum wavelength. So the X-ray energy is also equivalent to the energy as a result of the potential difference across the terminal of the cathode ray. So the minimum X-ray wavelength is equals to HC all over EV. So what the question asks us to find is the ratio of the de Broglie wavelength of the electron to the minimum wavelength of the X-ray. Now, if we want to write this ratio now, it means we'll have de Broglie wavelength of the electron, which is lambda E, all over the minimum wavelength of the X-ray radiation, which is lambda minimum, will be equals to this H all over square root of 2 mass of electron, charge on electron, the voltage applied, divided by HC all over EB. Okay, if we turn this division to multiplication, we are going to have H all over square root of 2 mass of electron, charge on electron, the voltage applied, which is the potential difference, times this is going to be EV all divided by HC, which is a speed of light. So this we cancel this. Okay, now if we simplify this, we are going to have a charge on electron, the voltage, all divided by square root. This is speed of light here, square root of 2 mass of electron, charge on electron, the voltage applied. Now, if we want to take these two into the square root, we can also rewrite these two as E squared, the voltage squared, all square root, divided by speed of light, square root of 2 mass of electron, charge on electron, the voltage applied. Okay, now if we further simplify this, equation, we are going to have the de Broglie wavelength of the electron divided by the minimum wavelength of the X-ray radiation is equals to square root of everything here. We have 1 all over the speed of light, E squared, B squared, all divided by 2 mass of electron, charge on electron, the voltage. So if we simplify this, it will remain 1 here, this it will remain 1 here. Okay, so what we are going to have is 1 all over speed of light, square root of EB, which is the voltage, all over 2 times mass of electron. Okay, now if you look at everything, this is the equation where the charge on electron, we know that one to be 1.6 times 10 raised to power minus 19 coulomb. Then we know that the speed of light is approximately 3 times 10 raised to power 8 meter per seconds. We know that the mass of electron is 9.1 times 10 raised to power minus 31 kilogram. Substituting all this in the equation, haven't got the equation of the ratio of electron, the wavelength of the electron to the minimum wavelength of the X-ray. We have 1 over C is equals to square root of charge on electron, the voltage applied or potential difference, divided by 2 times mass of electron, where we know that the charge of electron is 1.6 times 10 raised to power minus 19 coulomb, and the speed of light is approximately 3 times 10 raised to the power 8 meter per second, and the mass of electron is 9.1 times 10 raised to the power minus 31. Substituting all these values in the equation, we are going to have 9.88 times 10 raised to the power minus 4 times square root of the voltage or potential difference applied across the terminal of the cathode ray tube, the X-ray tube. Okay, so that marks the end of that question. Let's move to the next question. Now, question for AIV states that an X-ray tube operates at 10 kilovolts. It says you find the ratio of the X-ray wavelength to that of the de Broglie wavelength associated with the incident radiation. Now, the initial question already makes life easy for this particular question. The wavelength of electron to the minimum wavelength of the X-ray radiation is 1.88 is 9.88 times 10 raised to the power minus 4 square root of the voltage applied, and we have been given the voltage applied to be 10 kilovolts. So 10 kilovolts, which is the same as 10 times 10 raised to the power 3 volts. Substituting this value, the ratio of the wavelength of electron to that of the minimum wavelength of the X-ray is 9.88 times 10 raised to the power minus 4 square root of 10 times 10 raised to the power 3, which is 10 raised to the power 4. And square root of 10 raised to the power 4 is 10 raised to the power 2 times 10 raised to the power 2. Applying the law of indices, we are going to have 9.88 times 10 raised to the power minus 2. So this ratio here is more or less like this, is approximately 10 all over, because this 9.88 is approximately 10 times 10 raised to the power minus 2, and that's approximately 10 all over 100. This will cancel this. So the ratio of the wavelength of electron to the minimum wavelength of the X-ray radiation is ratio 1 to 10. So this ratio of the wavelength of electron to that of minimum wavelength of this is ratio 1 to 10. Okay, that answers that question. So we can move to the next question. With question 4b states that a manufacturer manual of a violin shows that the heaviest and the lightest string have their linear densities of 6.0 and 0.58 kilogram per meter respectively. Assuming that the strings are of the same material, to determine the ratio of their radii. Okay, now you should know that they said these strings are of the same material. You will know that if you want to find the frequency, they say you should find the ratio of their radii. The frequency of this material is 1 all over 2 length of those violin divided by the square root of tension in the string all over the mass per unit length. So if they are of the same material, it is assumed that they will be giving us the same frequency. Okay, now if we look at this, the frequency 2FL will be equals to square root of tension. The tension in each of the string will be the mass times gravity, all divided by linear density. Okay, now if we square both sides, we are going to have a 4F squared L squared is equals to the mass times acceleration due to gravity divided by the linear density. Now, if we make the mass and the linear density subject of the formula, we are going to have a 4f squared L squared all divided by G is equals to the mass divided by the linear density. We are still heading somewhere. Now, what is mass? It is volume times density. And what is volume? For this violin, it's going to be the cross-sectional area times the length of the violin times density. Okay, and what will be the cross-sectional area that is going to lead us to the radius? That's going to be pi r squared L times density. So substituting all this into this equation, we have a 4f squared L squared all divided by G is equals to, the mass is now pi r squared L rho, which is density, divided by linear density. Okay, so we can see that this pi, the length of the violin, which is because they have the same length, the density, these are constants. We can decide to bring all these here. So we are going to have a 4f squared L squared all divided by pi L rho G is equals to r squared all over density. Okay, r squared all over linear density. So all these, they are constants. All these are what? Constants. Now, if these are constant, therefore, your radius 1 squared all over linear density of the first one is equals to the radius of the second one squared all over linear density of the second one. And we are told to find the ratio of their radii. Now, the linear density of the first one is 6.0 gram per meter, and the linear density of the second one is 0.58 kilogram per meter. Okay, now substituting this, we have r1 squared all over r2 squared is equals to mu1 all over mu2. Now let's substitute those values. So we have r1 squared all over r2 squared is equals to 6.0 divided by 0.58. So r1 squared divided by r2 squared is equals to 10.34. Okay, now if you want to find this ratio, we have r1 all over r2 is going to be square root of this 10.34. So r1 divided by r2, by the time we find the square root, is 3.2, and that's r1 all over r2 is approximately 3. Okay, therefore the ratio r1 to ratio what? r2 is approximately ratio 3 to 1. That answers that question. Then we can move to the next question. So, going to the concluding part, which is question 4C, which says that the voltage of electromagnetic wave traveling on a transmission line is given by the voltage is equals to 10 e raised to power alpha sine 4 pi times 10 raised to power 9 t minus 30 pi x, all representing the voltage. Okay, so the question now says that where x is the distance in meters from the transmitter, you shall find the frequency, wavelength, and the phase velocity of the wave. Then question 4CII says you shall find the voltage at x equals 2.1 times 10 to the power minus 2 centimeter, and at t equals 0.32 seconds. Now the question 4CII says if the amplitude of the wave is measured to be 2 volts, you should find alpha. This is representing a kind of wave equation, but for electromagnetic wave, expressing the voltage, which is a function of displacement, and time in terms of amplitude, which is 10 e raised to power minus alpha, and sine into bracket 4 pi times 10 raised to power 9 t minus 30 pi x, all in voltage. Okay, now the question says we should find the frequency. Now, if we understand the wave equation, we will know that V as a function of displacement and time is equals to the amplitude, which is the amplitude will be like the initial voltage, sine this will be 2 pi ft minus 2 pi x all over lambda times everything in voltage. So the unit is volt. Okay, now the question says we should find the frequency. So it means our 2 pi ft as seen here is the same thing as 4 pi times 10 to the power 9 t. T will cancel t. Okay, pi will cancel pi. 2 here 1, 2 here 2. So the frequency is simply 2 times 10 raised to the power 9 hertz. The second question says wavelength of the electromagnetic wave. So we can get the wavelength from here. Our 2 pi x all over lambda is the same thing as 30 pi x. X will cancel x. Pi here 1, pi here 1, 2 here 1, 2 in 30, 15. So if we cross multiply, the wavelength is going to be 1 all over 15 in meters. Then the last question now says we should find the phase velocity. The phase velocity v, which is equal to f lambda. And the frequency that we obtain is 2 times 10 raised to the power 9. The wavelength is 1 all over 15. So 1 all over 15, if we evaluate this, we are going to have evaluating this frequency times a wavelength, which is 2 times 10 to the power 9 times 1 all over 15, we are going to have 1.33 times 10 raised to power 8 meter per seconds. That marks the end of question 4CI. Then we'll be moving to 4CII. Question 4CII says when the displacement x is 2.1 times 10 raised to power minus 2 centimeter, you should know that we are to divide this by 100. The displacement is going to give you 2.1 times 10 raised to power minus 4 meter. And the time is 0.32 seconds, that we should find the voltage. Okay, so the voltage will give us Vxt will be equals to 10 e raised to power minus alpha sine 4 pi times 10 raised to power 9 excuse me, times time, which is 0.32, minus 30 pi times x, which is 2.1 times 10 raised to power minus 4 meter. Evaluating all the values that we have in the sign, we are going to have a 0.972675 times 10 e raised to power minus alpha. 10 times all this is going to give us 9.72675 e raised to power minus alpha. Now, the last question is now based on what we obtained in this question III here. The last question in this question II. The last question, which is question III, states that if the voltage measured, this V x bracket T is now 2 volts, that we should find the value of alpha. It means that 2 is equals to 9.72675 e raised to power minus alpha. Then our e raised to power minus alpha is 2 divided by 9.72675. We are told that if the voltage V as a function of displacement x and the time t is given as 2 volts, we should find the value of alpha. If we substitute the value of voltage in the subsequent answer that we get in the previous question, we'll have our 2 to be equals to 9.72675 e raised to power minus alpha. So if we make e raised to power minus alpha subject of the formula, we are going to have a 2 divided by this 9.72675. If we evaluate this value, we are going to get 0.2056. Now, if you introduce log to base e to both sides, we are going to have log to base e raised to power minus alpha is equals to log to base e 0.2056. And log e base e is going to give us 1 here. Minus will cancel minus. So we'll get our alpha to be 1.58. That marks the end of Physics 002. Meet me in the next class for Physics 003. Thank you.